This is section 5.5, graphs of sine and cosine functions. So first we want to make a table with the special values on the unit circle. Notice we include pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6 pi, 2 7 pi over 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, and 11 pi over 6. And then of course there's 2 pi or 0, which is the same on the unit circle. Now, what we want to do is get all the values of cosine for each of those and sine. Right? So we start with pi over 6. Cosine is root 3 over 2, sine is 1/2, pi over 4, cosine is pi over 2, root 2 over 2, sine is root 2 over 2, pi over 3, cosines half, sines root 3 over 2, and so on and so forth, right? So we want to have that, keep in mind those values, right? Don't have to write them down, but it's a good idea if you have them written down somewhere, if you make a table of cosine and sine values for all of those. Now, what we're going to do is we have a graph of these cosine and sine values on the unit circle, but we're going to translate that graph over to the xy plane. Remember that when we look at the unit circle, it's a length, yeah, and that length can go from in the positive direction over and over around the circle, and in the negative direction over and over around the circle. And so therefore there's cosine and sine values for any length from 0 to positive infinity, and then also from 0 to negative infinity. Any length, right? Remember, these are lengths around the unit circle. All right, and so we can then put them on the xy plane. If I were to graph, for example, the graph of f of x or y equals cosine of x, right? So I would be graphing points of the form x comma cosine x, yeah, which is in fact what we do. All right, now when we do that, we end up with what is called a cosine wave if we're graphing y equals cosine x. And the cosine wave has certain characteristics, right? So all you're going to do is just graph x comma cosine x for every point that you know, right? Of course, maybe not every point. So what we want to notice is that it's actually a cyclic wave. That means once we know what part of it looks like, then we can just append that same exact drawing after the end of wherever we finish graphing, right? And so it turns out that these numbers repeat every 2 pi. If you think of the unit circle, that's a fact, right? All these numbers, all these coordinates repeat every 2 pi. So cosine just repeats every 2 pi. Every 2 pi we get back to the same values of cosine. And so the period then is called 2 pi. That means the length which is required to cover all the values of sine and cosine. And then once we break up that 2 pi and then we just attach it next or to the right or to the left forever and ever and ever, that actually makes the whole cosine wave. Okay? All right, so some characteristics of the cosine wave. Okay, so we have what are called key points, and then we'll look at what those key points tell us. So one key point is the point 0, 1, right? That's a coordinate, and our cosine wave goes through there. That means the cosine of 0 is 1. We have the point pi over 2, 0, which of course it means cosine of pi over 2 is 0. We have the point pi over pi negative 1. We have the point 3 pi over 2, 0, and we have the point 2 pi, 1. And so notice if we were to graph this wave, we would start at 0, 1, the first key point, curve down towards pi over 2, 0, then below the x-axis to pi negative 1, then back to the x-axis to 3 pi over 2, 0, and then up above the x-axis to the point 2 pi, 1. And that's a full cycle. After that, if we were to take that figure from 0 to 2 pi and append it either to the left or to the right, it would just attach at the end of that figure that we have and continue again to the left and to the right. All right, so that's considered one full cycle from 0 to 2 pi. It doesn't have to be from 0 to 2 pi. We just it's just something that's people do. But it could be, for example, from negative pi over 2 to 3 pi over 2. To me, that actually makes more sense in my head. And here's the reason. So when I think about from negative pi over 2 to 3 pi over to pi over 2, I have like a hill that goes from negative pi over 2 to pi over 2 and has at the top the point 0, 1, which is one of the key points we just talked about. Okay, and so then my graph is made up of that hill, my period, from negative pi over 2 to pi over 2, and then from pi over 2 to 3 pi over 2, there's like a valley that falls below the x-axis, and it's really the same figure as the hill that I just looked at, but upside down. So I have a hill and a valley, 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 forever and ever and ever. Okay? All right. But that hill and the valley make up one period of the cosine function. Okay? All right. Now, why does it help me to see it that way? Because if I look at the y equals sine x, it's very similar. So let's take a look at some key points. So the key points are 0, 0, which means, of course, the cosine of 0 is 0. Pi over 2 comma 1, which means sine of pi over 2 is 1. Sine of 0 is 0. Sine of pi over 2 is 1. The point pi 0, sine of pi is 0. The point 3 pi over 2 comma negative 1, which represents that the sine of 3 pi over 2 is negative 1. And 2 pi 0, which means the sine of 2 pi is 0. All right, and so again, from 0 to pi, I have a hill, and right in the middle at pi over 2 is the top, and from pi to 2 pi, I have a valley, and right in the middle at 3 pi over 2 is the valley bottom. Okay, so it's exactly the same wave as I just looked at on the cosine, except it's shifted to the right pi over 2. That means the hill starts at 0 instead of at negative pi over 2. Okay, but otherwise it's exactly the same hill, valley repetition over and over again. All right, and it's good to know, right? If you have a hill goes from covers half the period, then it always covers half the period. And what we're going to be doing is in a few minutes or somewhere along on this section, shrinking that period and lengthening that period. And so it's good to think of it that way. Okay, all right. Let's take a look at some of the stuff that we've actually already talked about. Some characteristics of the graphs of y equals sine x and y equals cosine x. The domain is from negative infinity to infinity. The range is from negative 1 to 1, including negative 1 and 1. The period is 2 pi, which means every 2 pi the same graph repeats. Sine of x is an odd function. So its graph is symmetric with respect to the origin, which means if we flip it upside down, it looks like exactly the same graph with exactly the same y-intercept. And if we look at symbolically, odd means f of negative x is negative f of x. And if we think of sine, that would mean sine of negative x is negative sine x. And I think we've seen that before. Cosine x is an even function, so its graph is symmetric with respect to the y-axis, which means the sine wave is a mirror image, and the mirror is the y-axis. Yeah. In symbolic form, an even function is a function where f of negative x equals f of x. So cosine x then has to equal cosine of negative x. And if you just think of maybe like cosine of pi over 6 and cosine of negative pi over 6, they are equal in fact. All right. And the graphs of y equals sine x and y equals cosine x differ by a horizontal shift of pi over 2. Remember, the sine is exactly the same as the cosine, but shifted pi over 2 to the right. Or the cosine is the same as sine, shifted pi over 2 to the left. All right, now, think about, let's say the function y equals a times sine of the quantity bx minus c, closed quantity, plus d, which would mean that you're multiplying the whatever the wave is vertically by a, right? The plus d is a vertical shift. Do you guys remember shifting and all those things? And the b is actually a multiplier inside in the argument, so it's actually shrinks or stretches horizontally, but counterintuitively, which means if b is a 2, you're shrinking by half. And if b is a 1/3, you're actually multiplying or stretching it by a factor of 3. Okay, so some things we want to know. A is a vertical stretch or shrink. In trig, the absolute value of a is called the amplitude, and the distance from top to bottom point of the curve is 2 times the absolute value of a. If a is less than 0, the graph is reflected vertically over the x-axis, and if you've shifted, then it's over the shifted x-axis. B is a horizontal stretch or shrink, and the period is 2 pi over b. C over B is a horizontal shift. In trig, it's called a phase shift. D is a vertical shift. We just talked about that. One full cycle is given on the interval 0 is less than or equal to bx minus c is less than or equal to 2 pi. Or if you solve for x, c over b is less than or equal to x less than or equal to 2 pi plus c over b. The domain is from negative infinity to infinity, and the range is from negative absolute value of a plus d to the absolute value of a plus d. Okay, so we're going to apply some transformations, and we'll see that on the next video. So this will be the end of part 1 of section 5.5, and we'll look at some problems. I'll leave it there. We'll continue on the next